Welcome back to ECE 320A. Homework number 1. I've already had a question or two on that, so apparently it is working. It is active. I know that many of you have signed up for the mastering, but that's how you will submit homework. We're in chapter 10, and exam number 1 is actually now it's in the same month that we just started today. It's on the 24th. So that's about 3 weeks away. Today what I want to do is start where we finished last time, was with this complex power triangle, which is a very powerful tool. It looks very simple. It's geometry and trig, but it allows you to determine some of these average power relationships that are going to be essential for solving single-phase and three-phase power problems. Then we will get into an example where we will examine the source power. Is that absorbed? Is it supplied? We'll start maybe talking about these relative to the line and the load. One of your first homework problems, I think, is dealing with a two-terminal element where they give you time domain expressions for voltage and current. We'll work through one of those or look at that. We'll develop some of these complex power formulas for both if you have the current available or if you have the voltage available. And then maybe all you need is either the current or the voltage relative to that device. Hopefully we will then get into looking at multiple loads, although in this first complex power example that we will talk about, you could sort of view that as having two different loads, the line being one load and the load being a load. So it is sort of a two-load problem buried in the description of transmission line and load. Here's the complex power triangle, and I've tried to color code it, so if you brought your crayons, we're in luck. We have blue for, I don't know, do people see words or sounds in colors? Just curious. Anyway, today when I was thinking of this, I saw blue, the real power is blue. See, I've got them confused already. So now whenever I hear blue, I just think real power. What are the units of blue? I'm sorry, real power. Watts. Then you have green. That's the reactive power, and that's associated with whether you have something that's more inductive or more capacitive. If it's more inductive, then based on Eli, the current is lagging the voltage, which means that in this angle, if the current is lagging the voltage, theta sub I is less than theta sub V, which allows that theta angle to be positive. And that gives us a Q that's positive. In this diagram, I've illustrated it to be consistent with an inductive load, to have a positive Q value. And the units on Q, the reactive power, VARs. All of these powers are volt amperes, but we are giving them unique names to try to distinguish between what we are really referring to. Real power, horizontal, is watts. Vertical power or reactive power is VARs, volt amperes reactive. The hypotenuse on this right triangle, the real power and the reactive power are orthogonal. The hypotenuse on this right triangle is the complex power. It has a length, which we will call the apparent power, and it has an angle, theta. If we had a purely resistive load, what would that triangle look like? It would just be a flat line, wouldn't it? Maybe I shouldn't say that. You don't want a flat line, right? That means, never mind. But if you had real power, then this angle, the voltage and current are in phase, they're aligned, and you just have all of your complex power is real. You wouldn't have that green component in that triangle. But based on that triangle, I could give you information with a few variables, and you should be able to extract or derive all of the other pieces or parts to that complex triangle. If I gave you the real power and the reactive power, now all you have to do is get out your ruler and straight edge and draw a right triangle, and you have the complex power. And if you have your protractor, you could measure that angle. If I gave you the hypotenuse, and then I maybe gave you the power factor. Here I haven't identified it yet, but the power factor is hiding there as the cosine of theta. If I give you the power factor, and if I tell you it's lagging or leading, that will tell you the angle value, because you can do an inverse cosine of the power factor, and if it's lagging, then you know that angle was positive. If it's leading, you know that angle was negative. And if I gave you the reactive power and the power factor, again, you have the vertical piece and the angle, and you can back out the other information. If I give you the real power and the power factor, now you can obtain the entire triangle. Is that clear? All from, and you wondered why you took geometry and trig. It was all because of today. No, it wasn't all because of today, but it should help you with the material in this part of the class. Real power is the length of the hypotenuse, the apparent power, the magnitude of the complex power times the cosine of theta, or the magnitude of S times the power factor. The complex power, I sometimes or maybe won't always give that an overbar, but that's a complex number. It has units of volt amperes. And if you knew the voltage magnitude across the element and the current magnitude through that expressed in RMS, you would then have the apparent power. And that's what the power company is having to provide to you. And then if you know something about the power factor, or if you know the angle, then you know all the component parts of complex power. Similarly, there's the reactive power with units of volt amperes. That's just the hypotenuse times the sine of that angle. Q can be positive or negative. P, well, you could say you have a negative absorbed, but that's like saying you have a supplied power. If that, we'll get into that in a minute. Questions on the power triangle. Very powerful tool. I would just start drawing a triangle if somebody gave me some units and some powers, and then I would figure out what all I have as far as the parts. This is a flashback to the first day. Remember our quiz where you started breaking out and your heart started racing, and I was asking you what is the magnitude or the time domain expression for the voltage across those two elements on the right hand side. Here we could talk about this problem in terms of power, where the horizontal pieces are not very large, but you could think of that as a transmission line. That's now what you use to transmit this power to a load, and the load now is made up of two component parts. It has a real part and it has a reactive part. What would you expect the angle sine to be, S-I-G-N? If I said, what's the power factors, or the load, what's its power factors sine, S-I-G-N? Positive, because it's inductive, and that's what we would have. What we want to do is try to find now information about the complex power of the source. What is the source, this voltage source that's now operating at 220 volts RMS, and that's the one we've decided to be the reference, so we've assigned it to have an angle of 0 degrees. What's the complex power absorbed or supplied by that source? That's what we want to determine. And I'm going to quickly go through this because I know that's already in your notes, right, in terms of that figure. But let's just recall what our notation or the convention is. And this is just the passive sign convention. And I hope it's clear, but if you now have labeled this element, you've placed some polarity markings for the voltage and you've indicated a direction of current. Those polarities and currents may not correspond at all to what's going on, but that's how you're referring to them in your calculations. The passive sign convention said if the current enters that positive terminal before the current goes through the element, then we will consider that absorbed power as positive. That's just our definition. That's our convention. That's the passive sign convention. We're assuming that if the current goes into the positive terminal, that element is absorbing power. Now, we have generalized power in the previous lecture to be equal to this product of volts and currents, but the units have to be RMS, and those are phasors, and we take the voltage times the complex conjugate of the current of that element to obtain the complex power of that element. And if the current is going in that direction relative to the positive voltage terminal, then we would say that's a positive absorbed power. If it turns out that let's say the P ends up being negative, then that particular element is actually supplying that much power. It's absorbing a negative amount of power. Is that clear? Let's now slow down and work through this. Now, if we're dealing with the source, if I wanted to look at this particular way that I have it drawn, and I said, let me write it down. I'm going to say now the absorbed complex power of the source. I'm going to say that that's S bar sub S. And relative to this diagram that I have sketched, how do I complete the right-hand side of that formula for capital S bar sub S? Based on the passive sign convention, and I'm asking for how much power is absorbed by the source. Now I have to go and look at my voltage polarity labels and the direction of the current that I've labeled, and now answer that question. Negative? Positive? I knew I could flip a coin on this one. So now it's the power absorbed by the source is what I'm suggesting we want to find. If it's absorbed, then I need that current arrow to be going into the positive terminal before it goes through the element. That's not happening with our source, is it? If you drew a circle as your voltage source and said, okay, the current is, it's coming out of the positive terminal, it's not going in. Is that making sense? In this particular case, we would have this as minus V sub S phasor, I sub S phasor complex conjugate. So it's a negative of VI star for the way that we have labeled V sub S and I sub S in that diagram. That's the amount of absorbed complex power of the source, which really means that we could be saying, what is the supplied complex power, or the complex power supplied by the source? Maybe I'm not wording it in the best way, but now if we said, what is S sub S bar, this maybe is going to be really confusing since I'm using the same, so I'll say that's a hat. It's not the same S bar sub S, because now that one that I'm saying now is what I'm saying is supplied. What's the expression for this in terms of the V and the I that I have in my circuit diagram? Now it's positive, isn't it? This now would be V sub S bar, I sub S bar, star. Is it clear the distinction that I'm trying to make? You may have questions that ask how much power is absorbed by this circuit device, or how much power is supplied, and it's going to depend on how you have actually labeled that circuit. If we want to find this, we were given V sub S bar. That's okay in terms of computing the right-hand side. We need to now find that current, I sub S bar. How do we find that current? This circuit is very busy, but it's basically a pretty straightforward.
I just have a question. Do we have to put the I back?
Do we have to do what?
Because we got our V sub S R or whatever.
Yes.
RMS units, right?
Correct.
So does our I have to go RMS?
So now the question is, our V, our supplied voltage, is in RMS. That was given to us. We didn't have it in a time domain expression. Somebody just handed us that 220 volts RMS. Now the impedances are given. If we solved for I in our expression that might relate V and Z and I, the I will automatically come out in RMS units, because Ohm's law. V is equal to Ri. We are generalizing that now to have complex voltage and current. We now have V is equal to Zi. If V is in RMS, I will be in RMS. They have to be consistent units in Ohm's law. If you wanted to use maximum magnitudes in your phasors, then they would both be maximum magnitudes in your V is equal to Zi expression. But in all of these power formulas, or in most of them, I like to use RMS because then we don't have to worry about this factor of 1/2 that floats around or that appears. Did that answer your question? Where were we? Oh, trying to find I sub S as a phasor. Do you see how you would do that? Do you have a plan? You just have an impedance with a voltage dropped across it. You can find the current by simply dividing that voltage by the total impedance. Let's find our total impedance in this problem. Z total is 2 plus J1. That was the impedance of the transmission line, and we could call that little z sub L for if we needed a notation just for the impedance associated with the transmission line, plus we have 78 plus J59, which is our load impedance, and we might call that Z sub capital L. So now I'm distinguishing between lower and uppercase L's. Capital L is load, lowercase l is line. And that's designed to not be too difficult to add. We now have an 80-60 triangle, right? Or a 3-4-5 triangle, essentially. This is our total impedance. We can now use that to find the current. That whole circuit was in series. The current's going to be the same through everything, through our source, through our transmission line, through the load. I sub S is now V sub S as a phasor over Z sub T. Using the RMS units that we had for our voltage, that's just 220 at an angle of 0. Z sub T is 80 plus J60, and since we are all, well, I haven't verified this yet with your passports, but I'm assuming the majority of you are visual learners or like to see things visually. 80 plus J60 is screaming at me to sketch a triangle. Is it doing the same for you? No, I just plug it in my calculator. Duh. But if you don't, if you have a napkin and you're in an interview, you don't have to have, oh, I misplaced my calculator. I didn't know I was going to be tested during the interview. Well, they may say, can you tell me a little bit about this angle? Is it 90 degrees? Is it 45 degrees? Can you give me a ballpark? Well, now you could just take out your straw as your ruler, use that to draw your straight lines and maybe break it or put some marks on it so that you now have 6 units and 8 units. Boy, you've got it solved, right? As far as an angle. Now you have 80 and 60, which probably isn't very accurately sketched. And if I wanted to, here is the magnitude of that impedance, where the magnitude of that C sub T is 80 squared plus 60 squared square rooted, and that should end up being 100, and the angle theta sub Z is the inverse tangent. Okay, now you can pull out your calculator, of 60 over 80. But you know it's less than 45 degrees, right? And it's one of these standard angles, isn't it? Or one that you'll see floating around maybe in this class a lot. 37 degrees approximately. And that can now go into our formula for the current. And you might want to just remind yourself of what you have. That's now amps in RMS. And it's a complex phasor. It has a magnitude of 2.2 amps and an angle of minus 36 or 37. Does minus 37 seem correct or in the right direction for this circuit? Can you sort of check your work as you're working through this problem? Does minus 37 seem okay? Well, it's less than 45, but you drew it positive in your diagram. Well, that was the diagram for the impedance, wasn't it? And what kind of an impedance was it? It was inductive. And what do we know about inductive loads? The current lags the voltage. Our voltage angle was 0. The current angle is minus 37. Okay, it's looking more and more like that's in the right direction. Now we have all we need to compute the complex power, and I think I'm going to use it as the, scared me, as the supplied. So this one I had the caret on top of, I believe, right? So this is the supplied power. I'm going to call that then V sub S bar I sub S bar star. This is now 220 at 0 degrees and 2.2 at the negative of a negative, or plus 36.87. I had to take the conjugate of that current, so that I now have 484 at an angle, and there's the polar form of my complex power. And this is volt amperes supplied. And you can use Euler. You can take the cosine of that angle and the sine of that angle to obtain the fraction that's real and the fraction that's reactive. So that we now have 484 cosine of 37, which ends up being 387.2, plus J, 290.4 volt amperes. And now, if somebody wanted, you now have even more information. You now have the amount of power supplied, which is 387 watts. You have the reactive piece that is also supplied, and that's 290 magnetizing vars. So this is in watts, and that's in vars. And if you wanted to, you could sketch the power triangle. You now have 387, 290, and hopefully you can draw better than I can. And here is your hypotenuse, which is 484. This angle, oh, I need to go back to colors. Here was P, here was Q, and here was S. And this is consistent with what we know. We had that diagram as inductors, and Q is positive. This is indeed, oh boy, I knew I shouldn't have established some kind of color strategy, but this is now positive, which says that we have an inductive load. Questions on where that came from or how that was obtained? Now suppose that somebody wants to know what's the complex power associated with the load. We found the amount of power, the complex power supplied by the source. Now somebody wants to know, well, what am I actually using at the load? What's my real power? What's my reactive power? Do you have a strategy for that? There's many, many different ways of doing it. If we could find V sub L, we would have it, right? Because we already know the current. So now we want the complex power of the load. And if I label that S, capital S sub capital L bar, what right-hand side would I use? And I'm going to say, give me the power formula for absorbed power. Bless you. Bless you. Do you know the formula? V sub L, I sub L, and I sub L is the same as I sub S, isn't it? And it has a positive sign because the current is going into the positive terminal. We now know that this is positive, V sub L, I sub L star, and this is the same as the current that we just found, since everything is in series. Now we can say, okay, well, do I really have to find V sub L explicitly? No, not necessarily. Remember, we have this. Whoops. But V sub L is just the load impedance times the current going through it. And now we have Z sub L times a complex number times its conjugate. And what is that? Do you know what that represents? The magnitude of that complex number squared. Is everybody comfortable with that? If not, we'll pick up with that in just a minute. We already know what the magnitude of I sub S is, don't we? That was 2.2. We just have to square that and multiply it by our load impedance, which was a complex expression. Meaning we now can say that the complex power absorbed by the load is our complex impedance, 78 plus J59, times 2.2 squared. So now we're multiplying 78 and 59 by something a little bit bigger than 4, and that ends up being 377.52 plus J 285.56 volt amperes, where this is now the power of the load. This is the reactive power of the load. And we could, if we wanted to, write that in polar form or find the angle of the load, and then we could take the cosine of that to find the power factor of our load if we wanted to. This is now 473.36 at an angle of 37.12 volt amperes. Question?
Could you explain really quick how you got to only using the magnitude?
Good question. That's where I was trying to postpone until now. I wanted to finish this. The question was, where did I squared come from? I think. Is that the question? Why is it just the magnitude? So what I used right here is I had that. I had I sub S, a complex number, times I sub S's complex conjugate. So now if we look at that in terms of just complex numbers, I had an A plus JB times an A minus JB. This I could say was my I sub S, and this is I sub S star. Is that okay? And now I know that I have A squared plus JAB minus JAB plus J squared B squared with a minus sign. I have a minus J squared B squared but J squared is minus 1, and this ends up being A squared plus B squared, which is just the magnitude of A plus JB squared. So this is now the magnitude of I sub s squared. So when you have a complex number times its conjugate, you now have... Okay, I don't know how frequently that's ticking, but we're going to eclipse an hour pretty fast. So I need to speed up. Are there questions on this topic? Hopefully it will near the finish line. Yes, question.
I was just wondering why again are we using the complex conjugate?
So why are we using the complex conjugate? That was in an earlier lecture. And essentially, let's see if I can find that. If we go back, was it here? Sorry if you haven't taken your Dramamine this morning. But here is where that was derived or sort of demonstrated. We had P, which was the cosine of theta v minus theta sub I. Then we had plus JQ, which was sine theta sub v minus theta sub I. We can use Euler's formula to now collapse cosine plus j sine to just e to the j angle. So now we have v, I, those are just numbers, e to the j theta sub v minus theta sub I. If we collect those two pieces and associate the angle of our voltage with the magnitude of the voltage, the angle of our current with the magnitude of the angle, but now we have a negative of our current. And to obtain that from just the angle of the current, we can negate that by doing the complex conjugate. And that's how we justified this expression for complex power. So that's what you have to remember. It's VI star. Does that help? So complex power is VI star. Is that clear? So anytime you have the voltage and current of an element, you need to take the voltage phasor times the complex conjugate of the current phasor. Did that answer that question? That was where did we get, I think, the formula for complex power, which we continue to use, so you want to be comfortable with that, but it's just VI star, where V and I are both in RMS and they're phasors. If it's a pure resistor, then you know that their angles are aligned or they're in phase, and that conjugate you could not worry about. And that then defaults back to what power is in a resistive circuit, VI. Now, relative to this load, what's the power factor? This was sort of an aside, so let me label it as such. There was an aside, and I'll put that in the cloud. Everything's in the cloud these days, so we'll put that information in the cloud, and if you need it, you can just pull it out of the cloud, right? Where was I? Oh, power factor. So now we have the power factor of the load, not the source, not the transmission line, the power factor of the load. And if you forget some of these, just go back to what we have said we're working with. The power expression is V magnitude, I magnitude in RMS, cosine of the angle between the voltage and the current. And in this case, this piece is the power factor, and that's the power factor of the load. What is this or what could you call that piece? Magnitude of V times the magnitude of I. The apparent power of the load, if somebody wanted to know. Who knows what people will want to know. But now we can compute the power factor of the load. That's just P sub L over VL I sub S bar, or that's just cosine of theta sub L, and we calculated in the polar form of our complex power of our load, we know its angle. That's this 37.1 degrees. We can just take the cosine of that and obtain a number, but you need more than a number for a power factor. You need two pieces of information. Don't forget, if I say power factor and you give me a number, it's not quite correct. And if I was really mean, it's not correct at all. So you need more than the number. You need whether it's leading or lagging. Here, if you find the cosine of 37.1, you obtain 0.798. Is it lagging or leading, that power factor? And how do you know? Because you take the cosine of an angle, that angle could be positive or negative. The cosine is just going to give you a number, isn't it? As long as you're in plus and minus 90. That sine of the angle is going to disappear when you take the cosine. So you have to basically tell us what was happening. Was this load inductive or was it capacitive in nature? It was inductive, so that means Eli, doesn't it? And where's I in Eli? It's lagging the voltage. So this was a power factor of our load is 0.798 lagging. Questions on that? Yes. Yes, so the question was, do we assume it was inductive because there were only inductors in the circuit? That's one answer. I could have tricked you by making those inductors have a negative reactance. And then it really effectively was a capacitive load that, for whatever reason, Tharp labeled as, or drew as an inductor. So the real reason that we knew it was inductive, well, one is because it was J59, that was positive. The other is that when we came here, whoops, Q was positive. And Q, we know, corresponds to a positive angle. A positive angle means that theta sub V minus theta sub I is positive, or theta sub I is less than theta sub V. So the current is lagging the voltage. So you can answer it many different ways. And it's just whichever one you like to think about. Q was positive, it was an inductor, the reactance was positive, theta sub V was bigger than theta sub I. All of those are ways to justify that it was a lagging power factor. Yes?
Are you always concerned with what the current is with the relation to the voltage?
Yes, so in a power factor, that second piece of the complete information in the power factor is telling you what the current is doing relative to the voltage. The current is lagging the voltage. The current is leading the voltage. That word is telling you what the current is doing relative to the voltage. Other questions? Let's look at the complex power. of the line, which really that's an abbreviation of the transmission line. I'm just being short. How could we find this? And many times in engineering, you can find answers many different ways. Wow, is that going uphill? Sorry. That's bothering me. But I guess it was because my line above it was kind of going uphill, so I was following the line. Sorry. Was following the line. Who's going? Never mind. How do... Was that? Anyway, how do we find the complex power of the transmission line? What's a way? The same thing you just did, correct, except with the impedances of the transmission line. So let's solve it a different way. Yes? Exactly. Did everybody hear that? You have complex power in this circuit. Some of that power is supplied, some is absorbed. The supplied has to equal the absorbed. The transmission line and the load are all absorbing power. The supply or the voltage source is supplying all of that power. If we want to know what the transmission line is needing or absorbing, we can compare the source, what it's supplying, with how much was demanded by the load. And that difference will tell us how much was absorbed by the transmission line. Does that make sense? Meaning, complex power of the line, we could say, is the complex power of the transmission line is the complex power supplied by the source minus the complex power absorbed by the load. And then we don't have to do all this multiplication. We can just do some subtraction with complex numbers. We have supplied of 387.2 plus J290.4. We're taking away, or we're using most of that in the load, which is 377.52 plus J285.56. So that we now have 9.68 watts being consumed by the transmission line or absorbed by the transmission line plus J484 reactive power absorbed by the transmission line. And now do you see why you might want to elevate the voltage? If you're trying to supply some facility that's quite a ways away and you don't have very effective transmission lines and there's a lot of resistance in that transmission line, you may want to get the voltage really high so that the total power is still VI star, but the current is small so that your I squared R loss is small if you have this transmission line represented by a resistor. Then the smaller your current, the less you're going to lose in real power delivering that power from the source to the load. In terms of efficiency, you're trying to reduce this power absorbed in your transmission line. Now, the power company is concerned about the bottom line, which means that they could care less if you're using a fractional amount of what they're supplying. They're going to charge you for what they're supplying. apparently you're using this much power. So they're going to charge you for the apparent power. What's the apparent power of the source? It's somewhere in all of our calculations. You don't remember? 484, wasn't it? It was the length of the hypotenuse of the complex power triangle associated with the source. That's the apparent power. We could find that many different ways. We could just go back and look at the triangle. We could also say, well, we've just calculated, let's check our work. We just were given the magnitude of the voltage supply. We calculated the current's magnitude. This is now 220. That was 2.2. So this is now the apparent power of our source. We could also calculate the power factor at the source, which is different than the power factor at the load. What was the angle of our source, where the angle now is theta sub v of the source minus theta sub I at the source. This is now cosine. What was that angle? Am I done? Cosine of the angle. What else? I need to tell you whether it's lagging or leading, where that current is lagging or leading. Is it lagging or leading? This was positive, wasn't it? Which now says, I'm running out of room, that that power factor was lagging. Do you see how much I could ask you on one problem? And that was an easy problem. Wait until I give you 10 loads with the source. Exam 1 is when? 24th of September. You have a few days to practice, okay? Pull out and start practicing, honing up your complex number skills and drawing. Let's look at an example that you might want to be comfortable with relative to your homework assignment. Suppose I give you a two-terminal device that I'm now saying, okay, here are the voltage terminals, and I'll label the upper one positive. There's my V of t, and let's say that the current is I of t. And we want to find the complex power for this element, where now I'm going to give you V of t. Suppose V of t is 100 cosine omega t plus 15 degrees volts. And let's say that I of t is 4 sine omega t minus 15 degrees amps. Now I'm giving this in time domain form, your voltage and current. Now what do you need to keep track of? is this two-terminal element resistive or purely resistive? How do we know? First, we probably want to get these either in cosines or sines, and then we'll answer the question, right? We want them both to be in, let's say, cosines. Let's all agree that we'll express these time domain expressions in cosine form. We now need to convert our current into a cosine expression. If we do that, whoops, let me just say that that's I'll do the hard part. Now what? Minus 90 degrees, right? So now, and you could always go back if you forget this, you could derive it with Euler, you could check this many different ways. You could draw cosine and sine and say, how are these related? The sine is actually lagging the cosine by 90 degrees. They are orthogonal. So now we have that this sine wave has an angle of minus 105 degrees in the cosine expression. The voltage is cosine. Now I can answer your question, is this two-terminal element purely resistive? And what are you looking for if it's purely resistive? Their voltage and current need to be lined up, don't they? They have to have the same phase. These do not have the same phase, they're out of phase. So if you were multiplying these as time domain expressions, your voltage humps and your current humps are going to be shifted in time. And now you can see that the product of I and V is going to have some negative piece, some positive piece, some negative piece, because you're multiplying these as a function of time. What was I trying to find? Luckily, I haven't scrolled that far up. The complex power. So the complex power, I can find the P and the Q with respect to this two-terminal element based on this information. The only thing that I have to keep track of now is the fact that this, unless stated otherwise, it's a maximum or a peak magnitude, isn't it? As is this. And if those are in peak values or in units of peak, now if I wanted the average power or the real power of that two-terminal device, I now have plus, since the passive sign convention is in effect, right? I have a positive, since I is going into the positive voltage terminal, I now have plus, and since these are in peak units, there's the 1/2. 1/2 Vm Im cosine of what? Theta V minus theta I. And I have all of that information. I now have that that's 1/2. Vm was 100. Im was 4 cosine of 15 minus a minus 105. Or this is now 400 divided by 2, or 200. Cosine of 120, that's a little bit beyond 90, so it's now negative, and it's a half in value. So this is now minus 100 watts. And by the sign convention that we had started with, that's absorbed power, which really means that that two-terminal element is supplying 100 watts to the rest of whatever it's connected to. What about the reactive power? Now we have all of the pieces. We can just follow the same strategy. This ends up being 200 sine of 120 degrees, and that ends up being 173.2 VARs, and that also is absorbed. Which now says that for that two-terminal element, if I write this in a sentence, the element is delivering 100 watts to the rest of the system, whatever is connected to those two terminals. And absorbing since it was positive, magnetizing VARs at its terminals. Or that two-terminal device, I'll just say element, complex power of that element is minus 100 plus J 173.2 volt amperes absorbed. And that should get you where you need to go on one of your homework problems. You may have to do it several times, but now you know the strategy. Question? So magnetizing VARs, that's consistent with a positive Q. So now you are basically storing energy in this inductive or in this magnetic field due to this inductor. So that's sort of like a magnet. If you wrap a bunch of wire around some iron core and energize that core, you're magnetizing that iron bar. So that's where this magnetizing is coming from. You just have a magnetizing personality when you're dealing with these power problems. Just think of it that way. Yes. So now you could say it's, I don't know, negative magnet. It's now basically you're storing energy. I like to just say you're storing energy in the magnetic field, or you're storing energy in the electric field when it's capacitive. But a lot of times you'll see with many industrial facilities, they are mostly inductive, and so that's why this magnetizing VARs is maybe more common than what happens. So now what you may want to do, though, is you may want to put in some capacitive load so that you get rid of some of that magnetizing VARs. You're trying to lower that by sort of sharing that back and forth closer to the load with this capacitor bank. And we'll get to that point a little bit later. Other questions? Let's now talk about different formulas for these complex power expressions. And we've already derived one of those in solving this earlier problem. We have the complex power is V RMS, I RMS, conjugate. I was waiting for correction. But that's VI star. We know that V is Z I RMS times I RMS star. And earlier today, we learned that we could collapse a complex number times its conjugate as the magnitude of that complex number squared. Which means that if somebody knows the magnitude of the current flowing through a certain impedance, you don't have to know the angle of that current. You can just take its magnitude, square it, and multiply it by that impedance, and that will give you the complex power of that impedance. Now you could expand that impedance into its component parts, R plus JX. And now we know that R times I RMS squared plus JX I RMS squared will produce the P, the real power, and the reactive power associated with that complex impedance. So that P now, in terms of current, if you know the current going through a resistor, you can just take the magnitude of that current, square it, and multiply it by the resistance, and you now have the power, the real power of that resistor, or that load. If it's a generic impedance, you just need to take the real part of that impedance. Similarly, you could now say that I RMS squared times X is the reactive power, and I will refer to these, I hope for obvious reasons, as our current formulas. Somebody could say, oh, I know the current going through that impedance. Oh, I can find the complex power of that impedance because all I need is the magnitude of that current. As long as I know my impedance is R plus JX, and X might be omega L, it might be 1 over omega C, depending on what you have, inductor or capacitor. If we have these current formulas, it's begging us to find the complement of that, which are these voltage formulas. And now we just have to express Ohm's law a little bit differently, but we're starting with exactly the same expression, VI star. It's just now we want our end result to end up in terms of voltages. So we leave the voltage alone and we rewrite the current as V over Z, but we have to take the complex conjugate of that current, which is V over Z. We now have to conjugate both V and Z in this expression. So that we now have, in terms of a formula, we have V RMS bar star over Z star. And now we have S is equal to the square of the voltage divided by the complex conjugate of our impedance to obtain the voltage expression. So somebody might tell you, they maybe have gone out and they found the magnitude of the voltage across that impedance, and maybe they know what the impedance is. Now you can express the complex power. You take the voltage in RMS, find its magnitude, square it, and divide it by the conjugate of your impedance. Questions on that? Then we will move forward. Let's now look at what happens when we have multiple loads, or we now are looking at total complex power in a network. And here, I probably shouldn't put this in brackets because this is one of the beauties of playing with power. Well, you need to be careful if you're playing with power, but you already know that since you're taking this class. You're trying to learn the right way to do it. But how these loads are interconnected, irrelevant. You can now take all of these different loads, no matter how they're interconnected, and add up their real parts and their reactive parts, and the sum of those two give you the total complex power, irrespective of how they're connected in series or parallel. That's what I'm trying to say in brackets. In. I better finish, huh? The interconnection structure, be that series or parallel, is unimportant. Suppose we let subsystem L have complex power S sub L equal to P sub L plus J Q sub L. That's the Lth subsystem. For an N subsystem network, we now have Nevada N subsystems in our total network. If we wanted to find the total power, we just sum up all of those P's. So we now have P sub 1, P sub 2, up to P sub n, and obviously we need to account for the signs, SIGN, of those powers. Some of those powers might be supplied, some might be absorbed. But if you account for all of those, then the total power would be just their sum, no matter how these loads are interconnected. Likewise, the total reactive power is now the sum of these Q's. And it will have units of VARs. Then we can simply say the total complex power of that N subsystem network is just P sub T plus J Q sub T volt amperes. And if you wanted to, you could go back to what we had done before. What I want you to leave with, though, is this caution. The magnitude of the total complex power is not equal to the sum of the magnitudes of the complex power. And now just start drawing some triangles where the horizontal lines are your P's, the vertical lines are your Q's, and see if your total hypotenuse ends up being equal to the length of all of those sub-apparent powers. We'll pick up at that point on Thursday.